longitudinal vibration and undamped transverse vibration. Okay, damped transverse vibration rather. Okay, so we are going to conduct two experiments. So regarding vibrations basics, we have learnt in our previous lab class, correct? So again, vibration is to and from motion of a system is called vibration. Then we learnt about number of cycles per second will give you the frequency of vibration, and we learnt about amplitude of vibration, and then we learnt about damped and undamped vibrations. What is damped vibration? When you have resistance for vibration, then we call it as damping, which essentially reduces the amplitude of vibration. And then we learnt about various types of damping characteristics like underdamped system, overdamped system, and critically damped system. So again, we learned that the critically damped systems are very, very essential for the during the use of large guns. After firing, it has to come back to steady state within short span of time. So there they use critically damped systems. Okay, that is what is called that is, if your damping factor epsilon is equal to 1, then we say that the system is critically damped system. Okay, and it is used mainly in bringing large guns to steady state within a short span of time. Okay, fine. So that's what we learned about damped vibration system. Undamping is there is no resistance for vibration, is called undamped system. Okay, and then we learned about free and forced vibrations. So free vibrations are the one wherein we give initial displacement and the system continue to vibrate forever. Okay, but theoretically that way, but practically it does not, because it stops because of friction in air. Okay, or air friction or air damping. Okay, so the free vibrations are the one which will, after giving initial displacement, it keeps vibrating on its own. Whereas the forced vibration, as long as there is force applied, like for example, for an electric motor or electric calling bell, as long as electric circuit is there, it will keep ringing or it will keep vibrating. Otherwise, it will stop. Once you take out your finger from the button, it will stop ringing. Okay, that's what the best example for forced vibration. And then we learned about longitudinal vibration and transverse vibration. In longitudinal vibration, vibration takes place along the axis or parallel to the axis of the member, whereas in transverse vibration, the vibration will be almost perpendicular to the axis of the member. That is what is called as transverse vibration. In torsional vibration, what will happen? The beam gets twisted and untwisted alternatively. Okay, so then the member is said to be in the torsional vibration. So these are the things. Are you there with me? These are the basics that we learned during our previous class. Are you with me? Are you with me?
Yes, sir. Yes, sir.
Yeah. Now we are going to conduct two experiments. One is undamped longitudinal vibration, another is damped transverse vibration. Okay. So for that, I'll show you the setup first. How a setup looks like. Yeah, can you see the screen there? Can you see the setup?
Yes, sir.
There's a figure here. Yeah. Can you see this figure? What is this that you are
Yes,
seeing?
sir.
What is this that you are seeing here?
So we can see a spring, protector or angle measurement device and shaft.
There's a scale over here and there's a spring. There are two experiments in the same setup. Can you see what is written at the bottom there?
No, sir.
It is spring mass system and this is simple pendulum setup. Okay, so this is simple pendulum setup and this is the spring, the undamped longitudinal vibration of a spring mass system. So here it's going to be spring mass system. This is going to be simple pendulum setup to find out the damped vibrations under transverse vibrations condition. Okay, so first what we are going to see is undamped longitudinal vibrations. That is essentially a spring mass system. We are going to find out the theoretical frequency and compare that with experimental frequency. Are you with me? Are you with me? Yeah? Are you with me?
Yes, sir.
Okay. Now, if you look at this sketch, this figure, okay, this is the figure that I have taken, correct?
Yes, sir.
Yeah, this is the setup. Yeah, this is the spring mass system where we are going to find out the theoretical frequency for a spring mass system and then compare it with the experimental frequency. Okay, are you with me? So to do that, what we need to do is initially we are going to take the free length of the spring. What is free length of the spring? We have discussed in previous class. What do you understand by free length of spring?
So the
It is
length
the
of the
length
string
of
and
the,
Yeah.
so it is the length of the spring when there is no mass attached to it.
Okay. So in the length of spring in unloaded condition. Okay. So we are going to note down the length of spring in unloaded condition. Then we apply load through a pan. Can you see the pan here? Pan and weight. So put together, so we have to consider weight of the pan also. Pan weight is 230 grams and weight that is attached is 200 grams. When you attach these two, what's happening to the spring here? Compared to this figure, what's happening to the spring here?
It's extended in length.
It is extended in length. Okay, so there is going to be deformation. As I said in the previous class, any system can be converted into a simple spring and mass system to find out the natural frequency of the system, which is very essential, okay, to avoid catastrophic failure when resonance occurs. Okay, so the entire spring mass here can be taken as a car's spring and mass together. So you can convert a system into a single degree of freedom system or 2 degrees of freedom system or multiple degrees of freedom system, finally to find out natural frequency of the system. Okay, so here after the attachment of weight here, there is going to be deformation. So we are going to take the deformation length also, that is going to be called as final length of the spring. This is the initial length of the spring. This is the final length of the spring. Difference between these two will give us the static deflection. Okay, are you there with me? Are you there? Okay, so when you come here, the initial length of the spring is 105 mm. After attaching mass and spring put together is 0.43 kg. The final length of the spring is going to be 226 mm. So the 226 minus 105 will give you the value of static deflection delta. That is LF minus LI will give you the deflection delta, and the theoretical frequency is given by 1 by 2 pi root G by delta, G is 9.81 meter per second square. Convert it into millimeter so that delta also will be in millimeter or either way. Okay. Get me the value of theoretical frequency, okay, for a free length of 105 mm, final length with 0.43 kg load is 226 mm. Okay, then you find out difference between them is delta, substitute in the equation and get me the theoretical frequency. So before that, note down the title of the experiment, that is vibration of spring mass system, undamped condition or undamped free vibrations of spring mass system. We can do that, we can take that way. Can you see the screen clearly in your systems?
Yes, sir.
Yeah. Please note down the aim of the experiment is to determine the natural frequency of vibrations experimentally and compare with theoretical value, or find out the natural frequency theoretically and compare them with experimental value. Okay, so that will be more apt because we are doing theoretical calculation first, then go for experimentation. Anyway, there is no hard and fast rule, so can keep it as it is. Note down the observations, note down the calculations or equations. Finished, huh?
Yes, sir.
Have you noted down?
Yes, sir.
Okay. Now, okay. So initial length of the spring is 105 mm. Final length after attaching 0.43 kg mass. Elongation of the spring is 226 mm. Find out theoretical frequency of this. Delta will be 226 minus 105. Okay. How much it is? 226 minus 105 is how much? Sorry, 175 for 0.43 kg. Okay. It is 175 mm is the final length of the spring for 0.43 kg. 105 mm is the initial spring length in unloaded condition. So difference is going to be 70 mm. Okay. So for 70 mm, that is the static deflection. What is the theoretical frequency? Please give me theoretical frequency. Theoretical frequency I require.
Sir, is it 0.06?
0.06.
06,
Just check.
like 0.0595.
No.
Sir, is it 1.884?
1.884, that's correct. Tirumani Shetty, check. Theoretical frequency is 1.884 hertz. What happened, Tirumani Shetty? What calculations you have done? G, how much you have used, Tirumani?
9.81, sir.
Hey, when you are using millimeter down there, how you can use
Oh,
9.81?
yeah, got it.
9810 and then 70 mm down, or convert 70 mm to meter and then so on. Either way is okay. Are you getting
Yes, sir.
1.884? Are you getting that? Rishabh Pandey, are you getting the value?
Yes, sir.
Roshan.
Yes, sir.
Next, for the final length of the spring is 226 for 0.630 kg. 0.630 is, that is, I attach another 200 grams over here. Okay. Then the elongation will be still larger. So that elongation for 630 grams of load. Okay. So here it was 200 grams. Here it was 400 grams. And pan weight is 230 grams. Okay. So put together is 630 grams or 0.63 kg, for which the final length of the spring is 226 mm. So with 226 final length, 105 mm initial length of the spring, get the theoretical frequency. 1 by 2 pi root G by delta.
1.433, sir.
1.433. Anybody else getting the same value?
Yes, sir. Same.
1 point? How much?
433.
1.433.
Okay. Right. So now theoretically we have found out the values of frequency. Correct? Anybody still doing? Anybody still want to calculate and find out? Sumuk, Sheikh Manan, Sharanaya, have you completed the calculation? Okay. All right. Now theoretical frequency is done. Now, okay, this is the theoretical frequency. Now experimental, how we do is, yeah, please look at the screen. Are you all seeing the screen now? Are you all seeing the screen?
Yes, sir.
Yes, sir.
Yeah. See, what you need to do is initially give initial displacement to this spring mass system. Are you there with me? Give initial displacement, that is stretch the spring down and leave it. It will start oscillating longitudinally. Okay? It will start oscillating longitudinally. Now, this is what you can see this, what you can call this as
Stopwatch.
stopwatch. Okay, so using the right button, if you press it, it will start working. Okay, note down using the stopwatch, note down time taken for 10 oscillations. That is, give initial displacement to the spring and mass and leave it. It will start vibrating longitudinally. Then using the stopwatch, okay, note down time taken for 10 oscillations, that is up and down, up and down, that is to and fro motion is one cycle. So note down time taken for 10 cycles. So in this case, for 0.430 load or 200 grams, that is the beginning one, 200 gram load, time taken for 10 oscillations is 7.06 seconds. Then find out time per oscillation, and then experimental frequency is 1 by time per oscillation, 1 by t. Okay, that will give you experimental frequency. Okay, are you there? Okay. Now find out the experimental value of frequency for 0.43 kg and 0.63 kg. Respectively for 10 oscillations it is 7.06 seconds and is 8.8 seconds. So find out time per oscillation, then 1 by t of it will give you experimental frequency. Give me this value.
So for 0.43 kgs, it is 1.42.
How much?
And for 0.630, it is 1.136.
42, and for 0.63 kg is 1 point. Correct? Are you there? Anybody not getting this value? Others, please calculate. Others, please calculate. And let me know whether this answer is correct or not. Are you getting these values?
Yes, sir.
Yes, sir.
Roshan Yadav, are you getting?
Yes, Sachin.
Shobit Katare,
Yes, sir.
what? Yes, Shobit, what are the values?
I'm doing calculations.
You said yes, and now you are telling you're doing calculation. Hey, what is this? I say, huh? Can't you do? You need so much time to do just one calculation.
No, sir.
See, if you are not interested, huh? What is the value, Shobit? Yeah, Shobit Katare. I want answer. Yeah, Shobit Katare.
So 1.42 only, sir.
Yeah.
1.42, sir.
What is that?
Frequency of experimental.
Okay. What is it for 0.63 kg?
Sir,
What is the value of experimental frequency for 0.630 kg?
1.136.
1 point.
136.
You are reading from the this thing, screen, or you have done?
Sir, I've used the calculator, sir.
Oh, excellent. Okay. Okay. Got it now as to how to do. Take initial length of the spring in unloaded condition. Okay. Weight of the pan is 230 grams. Weight attached is 200 grams. Apply that. Take the final length of the spring. Difference between final length and initial length of the spring will give you static deflection. So frequency of 1 by 2 pi root g by delta will give you the theoretical frequency. Okay. And then what you do is give initial displacement to this spring mass system and allow it to oscillate. Note down time taken for 10 oscillations. Okay. Note down time taken for 10 oscillations and find out what is the time per oscillation. Okay, that is divided by 10. Okay. So what you get is time per oscillation you get. So 1 by T will give you the experimental frequency of vibration for the system. Okay. Similarly, repeat the experiment by adding 200 grams more, take the final length, then take the difference between final length and initial length, and then take the static deflection and repeat the procedure and tabulate the results. Are you there with me? And this is the stopwatch that you can use it for counting time taken for 10 oscillations. Are you there? Are you with
Yes,
me?
yes, sir.
Yeah. Next experiment, you take down. All of you have noted down these answers. All of you have noted down the answers.
Yes, sir.
Yes, sir.
Okay. Right.
Sir,
Yeah.
sir, this time for 10 oscillation, sir, it doesn't depend on how much force we applied for giving that displacement.
Yeah, it does not matter. Okay, it does not matter. Okay, just give initial displacement and allow it to oscillate. Okay, so allow it to oscillate. Note down time taken for 10 oscillations. That's it. You can take time for 15 oscillations also. It will be still more accurate. That's all. Okay,
Yes, sir.
and divide the total time by 15, you will get time per oscillation. Reciprocal of that will give you the frequency experimental. Okay, are you there?
Yes, sir.
Okay, all of you have noted down these observations and calculations. Now we will move to undamped transverse vibration. Undamped transverse vibration. Note down, note down the aim of the experiment is to determine logarithmic decrement. It is actually damped transverse vibration. It's not undamped transverse vibration. Damped transverse vibrations to determine logarithmic decrement, damped frequency, critical damping coefficient, and damping ratio. Note down the aim and the tabular column. Have you noted down?
No, sir, 5 more minutes.
Yeah.
Done,
Yeah.
sir.
Okay. Now, how we conduct experiment? Let us see. Can you see the setup here? Can you see the setup?
Yes,
Right.
sir.
Yeah.
Yes, sir.
For this pendulum setup, attach a given mass. Okay. Attach a given mass. So one mass is 146 grams. Another mass is going to be 222 grams. Can you see that 222 written on that? So 146 and 222 grams. Okay. What you need to do is attach the mass and then take your hand and then bring it to some position. It will be graduated. It's a graduated scale with 80, 90, 100 and so on. So pull it to some known value of displacement. So that you call it as x1. Maybe you take it as 80 there and then leave the shaft. Okay, leave the shaft. It will keep on vibrating. The moment it goes and then comes back, note down the final displacement immediately, not after 4 5 oscillations. Leave that, note down the initial reading if it is at 80, leave it. This shaft will move that side and then come back. So when it comes back, it stops momentarily for momentarily at 146 grams. So when it comes back, it will graduate to 222 grams. Okay, so that is the setup. Okay, so 222 grams. 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 Yeah, are you people there? For so long there was any disconnection?
Yes, sir, we were here only.
Yes, sir.
Yes, sir.
Was
For
there
three
any
minutes.
You got disconnected.
Yes,
disconnection?
sir. There
Huh?
was disconnection.
From when it got disconnected?
So there was a disconnection. Uh, where you showed that we have to move the pendulum to 80 degrees. From
Oh,
there it
oh,
got.
okay, 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 okay. So there only it got cut. Okay, right. So what you need to do is attach the mass, okay, and pull it to 80 degrees initial displacement and leave it. This
You are
will
not
Excuse
only,
me,
sharing the
sir.
screen.
yeah.
You're not sharing the screen, sir.
Oh, not sharing the screen again. It's gone, huh? Oh, okay, 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 okay. Hmm. Hmm. Now can you see?
Yes,
Yes,
sir.
Yes,
sir.
sir.
Yes, sir.
Yeah. So what we need to do is attach a mass here. There's a threaded one, okay, shaft. There is a threaded shaft. So thread this mass to the shaft and then pull the shaft to maybe initial displacement. I take it as 80 and leave at that position. This entire shaft with mass will oscillate, okay, go there and then come back. Okay. So when it comes back for the first time, note down the final displacement on the graduated scale. Are you there with me? That is, attach a mass, pull it to 80 or 90 or 70, and then leave the system, leave it. So this fellow shaft with mass will go the other direction and then come back. When it comes back for the first time, note down that's going to be the final displacement. Are you with me? Are you with me?
Yes, sir.
Okay, so that's going to be initial and final displacements. Repeat the experiment, one with 146 grams, another with 222 grams. Okay, so this is what the setup is. So here, what you have to do is, that's how you have to conduct. So for 146 grams, 0.146 kg, initial displacement is 80, final displacement is 75, time taken for 10 oscillations is 10.01 seconds and time per oscillation is 1.001. Similarly, for 222 grams, 80, 70, 10.37 and 1.037 is the time per oscillation. So calculate logarithmic decrement, which is ratio of natural log of initial displacement to final displacement. T is time taken per oscillation. Put that here. Then for delta logarithmic decrement, you have found out. Substitute here and get the value of epsilon or damping factor. Then find out the natural frequency omega d by root 1 minus epsilon square. Substitute, find the critical damping coefficient, multiply that with the damping factor, you are going to get damping coefficient. Are you with me? Are you with me? Yeah, could you understand how to conduct the experiment?
Sir, I have a doubt.
Yeah.
When the pendulum we take it to 80 and
Yeah.
then leave it and it comes back, how is that equivalent to 10 oscillations?
No, no, no. That is you have that is for final displacement only. That is, initially you pull the shaft, okay, that's going to wherever you leave, that's going to be the initial displacement. When it goes and then comes back for the first time, that will give you the final displacement. And then allow it to oscillate on its own and then note down time for 10 oscillations. Got it? So this
Okay,
80 is
thank you, sir.
initial
Yes, thank you, sir.
displacement on graduated scale. When it does the first vibration, this is the final displacement on the graduated scale. Okay. So 80 by 75 are the 80 and 75 are initial and final displacement. Then allow it to oscillate and then note down time for 10 oscillations. Okay.
Okay, thank you, sir.
Yeah. Calculate the logarithmic decrement, damping frequency, damping factor, natural frequency, critical damping coefficient, and damping coefficient. Please calculate and let me know the answer. Did you complete the calculation? Yeah, did you finish? Did you finish? What's the value of delta?
So 0.0645 or
0.0645.
0.146 marks.
1 second. 0.0645, correct?
Yes, sir.
Yes, sir, correct.
Yes,
That's
sir.
correct. Next is
1.33, sir. Delta for the second one.
delta for the second one is 1.1.
0.133.
Okay. And
Omega is 6.276.
6.27.
276.
What is that?
Omega D.
Omega D. 6.276.
Yes, sir, for the first one.
Yeah.
And for the second one, it is 6.059.
Okay. What is the value of epsilon?
Epsilon for the first one, it is 0.0095.
0101.
Epsilon is equal to
0.01, sir.
0.0.
Sir, 0.0101.
Yeah, that's correct. 0.01. I got 0.0102. So 0.0101.
01.
Yeah. Okay.
And CC is
Yeah.
no. Oh man. Sir, CC is 1.83.
1.83 you're getting.
Yes.
Omega in how much you're getting?
6.27 only, sir.
6.27, sir.
Omega in
6.27.
6.27 you're getting.
27, yes, sir.
Mm,
And CC is 1.83.
just check the value of omega n.
Yes.
Omega d, how much you're getting?
6.276.
6.2.
Is
For
it
first
correct?
one, sir. For first one.
Is it correct? Omega d 2 pi by t. T is 1.037 is for 2. Okay. All right, calculate for both. Calculate all the parameters for both the readings. Okay. Yeah, did you calculate? Completed? What is the value of CC? What is the value of,
So for the first one, 1.83.
okay, second one? Yeah, 1 point
2.690.
for
83.
first one, huh? 1 point
Yes, sir. For 1.46 kg.
for 146 grams, is it?
Yes, sir. 1.83.
1.83, correct. Okay, 832 is what I got. Okay.
Sir, CC for second one 2.73, sir. Is it correct?
2.73 is correct. Yeah.
Okay.
For second one, it is 2.73. I got 2.69, but okay, 2.73, 2.69.
2.69, sir.
Yeah, 2.69 is what I got.
2.690.
2.69 for second case.
0.
Yeah. That's the value of CC. And natural frequency, we have found out it to be 6.27. Here already we have done.
For the second one, 6.06. It
Yes,
is the
sir.
same.
6.063.
6.059. Yeah, that's correct. 6.059 is the value of omega n, correct?
Yes, sir.
6.27 for the first one, 6.276 hertz for the first one. Second one is 6.059. That is omega n value, and omega d value for the first one it is 6.27. For the second one, how much it is?
6.059.
Yeah, that's correct. 6.059 hertz. Yeah. And what is the value of epsilon damping factor for second case?
0.0211.
0.0211. Correct? Okay. Anybody? Any doubt in this? Any doubt? Have you all finished with the calculation?
Yes, sir.
Okay. Shall I ask one of you to explain how to conduct spring mass system experiment? Yeah, anyone? Will anyone come forward to explain how spring mass system is experiment is conducted? Who will come forward? Nobody? Nilesh,
Yes, sir.
explain how spring mass system experiment, that spring mass system experiment is conducted in brief.
So the dam transverse one, sir.
Not damped, it is spring mass system, longitudinal undamped vibration.
So, okay. So we'll attach the, we'll first note down the free length of the spring.
Okay.
Then we'll attach the weight and we'll give the initial deflection.
Okay.
Then we will note the time for 10 oscillation of the
Now
spring.
before that, after attaching mass, we note down The
Final length of the spring is also.
length of the spring. Okay.
Yes, sir.
Then difference between those lengths will give us static deflection delta.
Yes.
Okay. Okay. Yeah, continue.
So then we note down the time taken for 10 oscillations,
Okay.
and we calculate the theoretical frequency using the formula 1 by 2 pi root g by delta,
Okay.
and experimental frequency using 1 by the time period. Time period is for one oscillation,
Okay.
and then we compare the results.
Experimental frequency. Okay. Next. Next transverse vibration. Whom shall Sagar? Sagar GB. Are you there? Sagar?
Yes, sir.
Can you please explain how the second experiment, that is damped transverse vibration experiment, is conducted?
Sir, we'll attach a mass to a shaft.
Okay.
Then we'll give initial displacement 80 degree.
Okay.
Then we'll measure initial and final position.
Okay. And note
Then
down.
we'll note time for 10.
Okay.
We'll note that. Then we'll note time for 10 oscillations.
Okay.
Then we'll do further calculations.
Okay. What are the things that we find out here? Delta is what?
Deflection.
No. In transverse vibration, damped transverse vibration, delta is called the logarithmic decrement. Ln of x1 by x2. If you remember, damped longitudinal vibration, we use delta to be logarithmic decrement. This is also damped transverse vibration, so therefore it is delta is logarithmic decrement. Okay. Then damped frequency, then damping factor, critical damping coefficient is Cc, damping coefficient is C value. Okay. Got it, Sagar?
Okay. Yes, sir.
Yeah, anybody? Any doubt in this? Any doubt you have? No doubt,
No,
huh?
sir.
Huh? Absolutely no doubt. Wait, I'll take attendance. Today is what, 29. Niharika?
Present, sir.
Venkat Sai?
Yes, sir.
Nikhil? Nikhil R? Nilesh? Neerab?
Present, sir.
Neerab?
Yes, sir. Yes, sir.
Patil? Present. But?
Present, sir.
Prajwal Bhatt? Prince Tonger? Rishabh Pandey?
Present, sir.
Rohan Pagalkar?
Present, sir.
Roshan Yadav?
Sir.
Sumant Sagar? Sumant Sagar? Sagar Dutt? Sagar Dutt Mathur?
Present, sir.
Sagar? Present. Sanjay Raghav? Sharanaya? Sheikh Manan? I think he is there.
Present, sir.
Yeah. Shobit Katare?
Present, sir.
Siddharth Shankar?
Present, sir.
Next is Siddharth Sridhar? Subramanya Gaonkar?
Present, sir.
Sumukh VR?
Yes, sir.
Rohan?
Yes, sir.
Okay. All right then. Okay. So next week we'll see with one more experiment. Okay.